Bismillah, salatu wassalam ala rasulillah. Okay, let's continue. Now we'll deal with the third method of reduction. We studied the algebraic simplification, the first method. Karnaugh Map was the second method. And now the third method is called the Quine-McCluskey Method. We'll still use exercises 4 to demonstrate the use of this method. As you remember, for exercise 4, we have 4 truth table. We will apply this method on table 1 and table 3. Okay, let's start. First thing first, we need to mention some characteristic of this method. Quine-McCluskey is practically similar to Karnaugh Map. Karnaugh Map is visual. Quine-McCluskey is tabular. Use tables. Use tables to do the reduction. The Quine-McCluskey method is a hierarchical method. It's used hierarchy. We do reduction variable by a variable, and each time we go up on the hierarchy. Okay, let's start with the first example. Okay, we have here the truth table, and we have here the table of the first stage. This is called the first stage. If you remember in the course, in the lecture we explained that this method is composed of two stages. The first stage is the creation of this table that represents the aggregation of a hierarchy. We have here mean terms. We will do some aggregation here. Aggregation means we are assembling two mean terms to reduce one variable, and we get here in the first pass mean terms with one variable eliminated. The second pass we have the aggregation of the previous pass, and we get two variables eliminated, the third pass, etc., etc. We will see that the condition to stop is where it is impossible to aggregate anymore. When we are impossible to aggregate anymore, we stop. We have as many paths as possible until it's still not possible to aggregate anymore. The aggregation, we told that on the lecture, is based on T10 theorem. We have this very important theorem. This theorem is very easy and very efficient. It's very efficient and is the same theorem used for Karnaugh Map too. If we take, for instance, two mean terms, let's take, for instance, this one and this one. We say that they are mean terms because their outputs are ones. We have two mean terms. This one is A, B, C, but we have to put a bar for each zero. We have bar here, bar here, bar here. Or we have the second mean term is A, B, C, and we have 0 here and 0 here, 0 for A and 0 for C. If we apply the 10 theorem, we can see that one variable changes. It's B. It's B bar here, and it's become B. The other are the same. A bar doesn't change. It's not eliminated. B is eliminated. C bar was not eliminated. This is the result. We call that aggregation. We do the assembly by elimination. We assembled those two and created this one. This one is called implicant. We call that implicant. And they are listed here in the first pass. In the second pass, we do the aggregation of other applicants with two variables, etc., etc. And you can see this is hierarchy. This is a hierarchy. We have a tree. We have reversed the tree of hierarchy. Anyway, let's start. This is the idea of this method. Now let's start the application. Let's see how we apply this method. Okay, let's start by the first column. The first column is this one. We have to list all the mean terms. How many mean terms do we have? We have 1, 2, 3, and 4. We have only 4 mean terms. We have only 4 mean term. We have a condition here. We have to group the mean terms by the number of ones inside. Let's see how we can do that. We have this first one, for instance. First one, this one has the value 0, binary. And it's written 0, 0, 0, like this. Here we can count, we have 0, 1s. We have 3, 0. Don't have any 1 here. We have the first group. The first group is composed of 0, 1. The second group here is the mean terms with only 1, 1. We need only 1, 1. For instance, this one contains only 1, 1. It's 10, the value 2 in binary, and it's written 10, like this. We have only 1, 1 here. This is the second group. This value, for instance, contains 2 1s, and this one, the last one, is 3 1s. We can conclude that we have 3 different groups. We have 3 different groups. I have to give this remark that this one is contain only 1 here, but it's not a mean term. If it was, let's suppose that if it was 1 here, it's a mean term. We have to add it in this group. We have to add it in this group. But in our exercises, it's not. We have only to add, to stop here. We have only 1 instance with 1, 1. We have, for this one, we have 2 1s. This is the value 3 in binary. Have to write it 0, 1, 1. And this is the only one. This is the only one in this group. And we have the last one is this one. What is it? Sorry. I did a mistake. We have 2 1s here. Okay, sorry. We have 2 1s here. We have to add it to the same group. Very good. Very good. We have a 1 here. We have this value, which is the value 6 with 2 1s too. We have 2 1s too. We have the first one and the second one. Okay, good. We finish here. We have our 4 mean terms. We created the first column. To pass to the next column, we have to compare each pair of groups. We have to compare this group with this group. If we are able to aggregate, to use the theorem T10 and eliminate one variable, we have to write it here, etc., etc. We have to first make the comparison between this group and this group. Second, this group with this group. Third, this group with other group, etc., etc., etc. The comparison is done this way. We have to compare the 2 adjacent groups. Those two, etc., etc., etc. If for each comparison we create a new group here. For instance, for those 2, we create a special group. This is group 1, for instance. When we compare this with this one, this group with this one, we create the second group. If we compare, for instance, this one with this one, we create the third group, etc., etc. Each group represents a pair of two comparison. Okay, very good. Let's see what we can do here. We have, if we compare, we have only one instance here, and we have only one instance here. We don't have the choice, we have to compare 0 with 2. And we can see that we are able to eliminate this variable. We have to eliminate the b. You have to remember that this is the b. It's the elimination of the variable b. Okay, we have to write this. We have to use 0 and 2. It's not used. We have to aggregate. The correct term is to say we have to aggregate this one with this one, and we will get 0 for A. We have dash B. It's eliminated. It's represented by a dash, and we have 0 here. Very good. And we have to write a V to tell that those two mean terms are aggregated, and they produce this one. We have to close the group here. Why? Because we have only one possible comparison. We compare this one with this one. We have only 2. We stop here. Okay, let's continue. Let's now compare this group with this group. And you have to create the second group. This is the creation of the second group in pass 1. Okay, you have to compare this one with this one, the 2 with the 3. And we can see that we have this variable that should be eliminated. And we have 2, aggregation of 2 and 3 that produces this value. We have dash here. The variable that was eliminated is this one, is C. Okay, very good. We have to put V here. This one was aggregated. V, it's applied for the mean terms or implicants that are aggregated in the next pass, in the next column. The second comparison is this one with this one. We have to do all the possible comparisons. We have to do all the possible comparisons. We have to compare this one with this one. Is it possible to reduce here? Yes, it's possible to reduce this variable, the variable A. Okay, very good. We have to write it. 2, 6. We have 2, 6. This way. That produces 2, 6. Produces dash 10. Dash, that means the A was eliminated, and what's left? It's left the value 10. Okay, very good. Very good. And we stop here. We stop here. We finished. We have to put a V here to tell that this mean term was implied in an aggregation. Okay, we finished pass 1. Let's try to do pass 2. Pass 2. The column pass 2 is different from this one forming the groups. Why? Because here, in this case, to reduce an implicant, we call that an implicant. To reduce an implicant, the 2 implicant should get the dash at the same position. Let's pretend that we are trying to reduce those 2 implicants. This is a necessary condition. The condition is that you can see that the dash is at position A. To be able to reduce here, it's obligatory. We are forced to choose the implicant with the dash at the same position. Here we can do a reduction, and we can reduce this variable. And we will get dash 1 dash, for instance. But if we have, for instance, a dash in a different position like this, for instance, here, in this situation, we cannot compare those 2. We cannot compare those 2. We have a condition that the dash should be at a specific position for the 2 comparison. This is why This is the reason that the groups created here for pass 2, pass 3, etc. and so on, starting from pass 2, here the group represents the position of the dash. For instance, this group represents dash at variable A. Here dash at variable B. Here the dash at variable C, etc., etc. This is the way how we form a group in pass 2 and pass 3 and the other passes. We respect what? The position of the dash to form the groups. It's different from what, in conclusion, you have to be aware of that. It's different from this one. Different from this one. This one, the groups are formed by the two previous compared group. For instance, this group represents the comparison of those two groups. This one is the comparison between those two, etc., etc. Okay, very good. Let's see if we have implicant with the same dash. This dash is at the second position, at position B. This one is at position C. This one is at position A. It's impossible to do any comparison, any aggregation. It's impossible to do any aggregation. It's not possible to do any aggregation. In this way, we are stuck. It's impossible to do more. We stop on pass 2. We are not able to go to pass 3. And we stop. This is the algorithm. The algorithm says that we stop when it's no more possible to aggregate. In this case, we are not possible to aggregate when a mean term or an implicant which is not aggregated in the next pass, we have to mark it as X, as a cross like this. Those three are not aggregated and we have to mark them. And this mark X is very important. It's very important. This is actually the result of this first stage. This is the first stage. And those three implicants represent the result of this stage. We can write them. We have no, it's not important to write them. Anyway, we marked them. We have 3. They represent the result of the first stage, and they are called prime implicant. Prime implicant. Prime implicants, or PI, or PI. The prime implicants are, we have here, let's write them. We have 0, 2, we have this 1, 2, 3, and we have this 1, 2, 6. The prime implicants are the primes are the implicants that cover all the mean terms. They cover all the mean terms. That means you can see that we have, for instance, we have 0, 2, 3, 6. You have to find it there. You can find, for instance, the 2 is here, the 0 is here, the 3 is here, this is 2 repeated, this is 2 repeated, the 6 is here. We have all mean terms represented here. They are reduced and they are represented on those prime implicants. But we can say that those prime implicants represent all the mean terms. represents all our function. If we are able to represent all min terms, that means we are representing all our function, Boolean function. Very good. Very good. At this position, we finish the first stage. This is the end of first stage. Let's pass now to the second stage. Let's pass to the second stage. The second stage, we have to draw a table called, I don't remember the name, how it was called, the prime implicant table. Prime implicant table. And it is designed this way. We have to put all our prime implicants in the rows. We have 3 prime implicants. We have to draw 3 rows representing each implicant. Okay, here we have the first prime implicant. Here we have the second one. And here what we have the third one. This way. Here we have prime implicants. And here we have mean terms. We have, okay, I don't have many space here. We have mean terms. Okay, very good. How many mean terms do we have? We have 4. We have 4 mean terms. We have the 0. We have the 2. We have the 3. And we have the 6. Okay, this way. Now, what we have to do, we have to mark each implicant which each mean term is covered. For instance, what we can say that this prime implicant, it's covered the 0 and the 2. It's covered this one and this one. This is the 0 and this is the 2. It's very easy. It's very easy. Okay, what do we have? We have, for instance, the 2. This implicant, it's covered the 2 and 3. It's very easy. You have this one, it's covered the 2 and the 6. This is what we call the table of the prime implicant table. It's very easy. It's very easy. What we get in this table, we get each mean term by which each implicant is covered. By which each implicant is covered. You can see here that all mean terms are covered here. But it's different. It's different. The second step is to extract what we call the essential prime implicant. Essential prime implicant. Okay, we have to put that here. And we have the essential essential prime implicant. What is the essential prime implicant? In this step, we are trying, we have the prime implicants. We have the prime implicants. Those prime implicants, they cover all the mean terms. They are sufficient to reduce the function, but we can observe that we have repetition. What does that mean? That means we can eliminate some prime implicant and at the same time get what's left that cover all the mean terms. For instance, let's suppose those two, it's not true, it's just supposition. Let's suppose those two are able to cover all the mean terms. If it's possible, we have to take the minimum. You have to remember here, we are trying to reduce. We have to get the minimum prime implicant possible to cover all the mean term. This is the goal, this is the purpose of the stage 2 of this method. We are trying to choose the minimum number of prime implicants that cover all the mean terms. We suppose that we don't need that, and those two are sufficient to cover all this. This is just supposition. We have a special method to find what we can delete and what we don't need to delete. The first thing, we have the essential prime implicants. This group, those prime implicants are essential. We are not able to delete them. If we delete them, we have a mean term, that is not covered. What does that mean? If we check the columns here, we have 4 columns. If we check the columns with only one x, like this one, we have one x here. In this column, we have only one x. In this one, we have 3. It's not included. And this one contains one column. What we can say that those x are essential. What does that mean? If I take for this x, for instance, this mean term is covered by this prime implicant. That means I cannot reduce this one. If I eliminate this one, there is no prime implicant that can cover this one. It's covered by only one prime implicant. This prime implicant is now, we call it essential. This one is essential. Essential means that it's not possible to delete it. It's not possible to delete this one. It's not possible to delete this one because it's covered this. This is the only one that's covered this mean term. It's the only one that's covered this mean term. Okay, very good. Let's look for the essential prime implicants. We have first one, this one. This one is essential because it's the only one that covers this mean term. You have to add it. We have the 0, 2 is an essential one. Next, let's see this one. This column. This mean term is covered only by this implicant. That means we cannot delete this one. It is essential. We have a 2, 3, an essential prime implicant. Let's continue. We have the last one. This column. This mean term is covered by this one. That means this one is essential too. And here we can say, okay, this group represents the essential prime implicant that we cannot delete. They are essential. We cannot delete. We have to use them. Imperatively, we are forced to use them. But in this situation, we are not fortunate. Why? Because all the prime implicants are essential. We can't delete anyone. We have to use the 3. And in this case, the method stops here. We cannot continue. We have to stop here because we are not able to delete any prime implicant. For these exercises, we are unfortunate. We were not able to delete any prime implicant. The three are essential, and you have to use the three for the solution. But you will see in the next exercises, we will be able to eliminate some prime implicant. For now, for these simple exercises, we have the three, and we have to extract the solution for upon those three prime implicant. The solution becomes very simple. We have to use the rules of mean terms, or the SOP, the sum of products. We have to use the rules of sum of products. That means for our f of A, B, C, we have this one, 0 on A and 0 on C, and B is eliminated. We have A bar because A is 0, and we have C bar because C is 0. Or the second one, we have 0, 1 dash. 0 for the A means bar, 1 for the B means not bar, dash means C is eliminated. And then the last one, we have dash mean A is eliminated, B1 means B without a bar, 0 means C with a bar. And this is our reduced function. And I can tell you, this is exactly the same result as we found with the Karnaugh map. The two methods are essentially the same method, only in some special cases, but in general, they are exactly the same method. Okay, we finished this exercise. We have to pass to the next. Okay, let's continue. Let's now see the next exercises. We will start with this truth table. Okay, here we will do exactly the same thing. What does that mean? We have to choose the mean terms with the output 1 like this. And we have to group those mean terms in this column. Of course, the groups are formed based on the number of ones. We'll start with the first group with no one at all. We have this value, which is the value 0. We have no one. Okay, this way. This is the first group. The second group with 1, like this one, for instance, and this one is not. This one has 2. Okay, this one, 8. We have 2 and 8. Okay, that's all. 2 and 8. We have 2. No, sorry, it's not 2. It's 1. Sorry. It's 1. Okay, this one, it's 1. 1, 0, 0, 0, 1. We have only 1. And we have the 8. Also with 1, 1. 8 is written this way. Okay, very good. We have to pass to the number with 2 ones, like this one. This is the value. Which one? Which is the value 3. We have 3. Okay, next we have this one. This is 6. We have 6. And we have, this is 8, this is 11, 3, 3 ones. Okay, we finished with 2 ones, the group of 2 ones. Let's go back to the group with 3 ones. Okay, we did this one is done, this one is done, this one is done. We left with this. This is the value 11. One, 0, 1, 1. This is the value 11. This is the value 13. 1, 1, 0, 1. And the last one, this is 14. This is 14. 1, 1, 1, 0. Very good. We finished the first column. The second column, we have to compare each adjacent groups. We have to compare this group with this one with this one, and this one with this one. Okay, let's compare this one with this one. We have to compare each value with the other ones. We have to browse, to go through all the possibilities. We have this one with this one, 0, 1. We can see that it's possible to delete the D here. We have to write 0, 1, and we have 0, 0, 0, dash. Of course, those two are marked by V. They are aggregated. We have to compare this one with this one. Yes, the 0 is the 8. We can compare the 0 with the 8. And this time we are deleting the A variable. Okay, pretty good. And we finished the first group here. This first group is the comparison between those two groups. Okay, let's continue. The next group is the comparison between those two groups. We have the first one. Sorry, you have to pick a V here. It's already aggregated. Okay, we have to compare the 1 with the 3. Is it possible to delete one variable? Yes, we can delete the variable C. We can delete the variable C. 1, 3. 1, 3. And we have to delete the variable C. We have 0, 0, dash 1. Very good. We have to compare the 1 with 6. Okay, sorry, we have to put this with V. And we have to compare this one with this one, and we can see it's impossible. We have too many variables that changes. We can delete here. Okay, we pass to the next one. We have the 8 with the 3. 8 with the 3. We have 3 variables that change. It's impossible. Okay, let's compare 8 with the 6. Same here. We have too many variables that change. We have 3 variables that change. It's impossible. Okay, very good. Very good. This one is not marked yet. This one is not marked yet. Anyway, comparing this group with this group, we arrived at this group. Okay, let's continue. We have to compare this one with this one. Let's start with the first one. We have to compare 3 with 11. Yes, it's possible. We are able to delete the value A. Okay. 3 with 11. 3 with 11. Okay, and we have to delete the A. We get 0, 1, 1. A 3 with 13. 3 with 13, we have many variables that change. A 3 with 14. Same here, we have many variables that change. Okay, let's continue. We have 6 with 11. Before I forgot, I have to mark the 11 as aggregated. We have to compare the 3 with, the 6 with 11. The 6 with 11, it's impossible. You have too many variables that changes. We have 6 with 13. We can see that 6 and 13, it's impossible to reduce to. We can't reduce. We have 6 with 14. Yes, it's possible to reduce with 6 with 14. It's the A that changes and we can delete it. 6 with 14. I have to write it 6 and 14. Okay, what do we get? We get A that is deleted, and we have this configuration. This is the last one. We have to mark 6 as V and 14 as V. The only one here which is not aggregated is the 13. This one is the prime implicant. This one is a prime implicant. Anyone with the X mark is a prime implicant. Okay, let's continue. We have to do the same here, but you have to remember, in past 2 we have an important condition. We need to respect the dash. The groups are organized around the position of the dash. We can, for instance, start with a dash at the first position, at D. Okay, this is the last position with D. Okay, we can check here, we have only one D. Yes, one dash as the D position, you have only one. That means this one, it's impossible to aggregate it with another one. It's unique, it's solitary. We cannot do that. Let's see the dash at the second position, at C. C is second position. Let's see how many implicant do we have with C at the second position. We have, I guess, one. We have only one. This one is not. This one is not. This one, okay, it's the same. We cannot delete it. This is a prime implicant. Okay, let's continue. The dash at the third position as B. This is not. We don't have anyone. Let's now see when the dash is at the last position at A. We have a 3. I guess we have a 3 implicants. Let's see if we can reduce here, if we can aggregate 2 of them. Okay, we have 3 possibilities. We have this one with this one, and we can see we cannot. We have 2 variables that change. We cannot do that. Cannot aggregate here. Let's combine this. Try to combine this one with this one. Same. We cannot. We have too many variables that changes. We cannot. Okay, let's continue. The last possibility is see this one and this one, and we can see it's impossible too. We have 2 variables that changes here. We cannot. That means that the 3 are prime implicant. And that means that we can now not go to the pass 2. We have to stop at pass 1. And in total, we have 1, 2, 3, 4, 5, 6 prime implicant. This is the result of pass 1, of, stage 1, the first stage. The first stage, we have 6 prime implicant, 6 pi. We have 6 pi. Okay, very good. The next step is a stage 2, the second stage, or stage 2. In second stage, we need to draw this table. This table, we said that represents, this is the prime implicant table, and that represents, that allow us to know which mean term is covered by which prime implicant. We have to write here the mean terms, and here we have to write the prime implicant. Okay. How many mean terms do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's start by 0. We have 0 here. 1. We have 3. We have 6. We have 8. We have 11. We have 13. And we have 14. We have 14. The prime implicant, we have many of them. We have this one, 0, 1. Zero, 1. We have 0, 8. We have 1, 3. We have 3, 11. Which dash 0, 1, 1. We have 6, 14. Which is dash 1, 1, 0. And we have the last one, this 1, 13. It's a mean term, but it is at the same time a prime implicant because it was not congregated. Okay, 13 we have to write without dash. Okay, very good. Now we have this table. We have to mark which mean term covered by which prime implicant. It's very easy. We have just to read the parentheses. We have this one, 0, 1, 0, 1. This one, 1, 3, 1, 3. This one, 3, 11, 3, 11. This one, 6, sorry. I did a mistake, sorry. Okay, this one is 0, 8. The second one is 0, 8. The third is 1, 3. 1, 3. I have to be careful here. 1, 3. 3, 11. 3, 11. We have this one, 6, 14. 6, 14. And we have 13. Okay, now we finished the covering of all mean terms. We have now to the The first step is trying to extract what we call the essential prime implicant. For this, we have to look for the columns with only one cross mark. Here we have 2, we have 2, we have 2, we have 1 here. This means from this column we need to extract one essential prime implicant. This one 2, have 1 cross. This one 2, we have 1 cross. This one 2, we have 1 cross. And this one 2, we have 1 cross. What we can say we know that this one, for instance, this is a prime implicant, essential prime implicant. We have to write it. Okay, this is the first one. The first one is 0.8. 0.8 dash 0 0 0. We have this one, for instance. This one is 311. 311 is essential prime implicant. 311 is dash 011 dash 011, and we have this one and this one. We can see that they share the same essential implicant, prime implicant. This is 614. We have 614, which is dash 110 110, and the last one you can see this is this one 13. This is okay, I have to make some space. This is 1 3, which is sorry, it's 13. It's 13. It's 13, which is 1101. Very good. We have the 4 essential prime implicants. Those guys are essential and they are imperative to be in the result. They are imperative. You cannot delete them in the solution. Now let's see what we can delete from what's left. What's left? We can see that this one, for instance, is left, and this one is left. Maybe we can reduce some of them. To know that, we have to continue our algorithm. We have to continue our method. We have to extract first the mean terms covered by those 4 essential prime implicants. We have to extract the mean terms covered by those 4. Okay, we have to delete this. Let's see how many mean terms are covered by those 4. We have this one, 0.8, is covering first the 0. Covering the 8, we will try to get right order. We have this one. Okay, we will try to get the right order. We have this one is 0. This one is covering this one, for instance. Yes, we can say we have a 3. have the value 3 is also covered by a prime implicant. We have the 6. We have the 6. We have this one, the 8. We have the 11. We have the 13. And we have the 14. Okay. We have here, how many 1? We have 1, 2, 3, 4, 5, 6, 7. Practically all the mean terms are covered by the essential prime implicant. Now we have to see what's left. What is not covered by the essential prime implicant? This bar means what is not covered by the essential prime implicant. Let's see, we have 0, 3, 6, 8, 11, 13, 14. Which one is not covered? I guess if you look at this, we have 3 is covered, 6 is covered, 0 is covered, the 1 is not covered. You can see that the 1 is not, doesn't belong to this set. The 1 is not covered. You can see here. Yes, the 1, you can tell that it's covered by the 2 non-essential prime implicants. Okay, very good. We find it. We have the 1, which is not covered. This is the process. You have to find which mean term is not covered by essential prime implicant. In this case, we have only 1. This is the 1 mean term. 0, 0, 0, 1. Very good. Now, we have to list the 2 left. We have to list the non-essential prime implicant. N means non-thus. The prime implicant that does not belong to this group. We know that, we already seen that before, and we marked them as X here. We have this one and this one. Those are the non-essential prime implicants. We have 0, 1, 0, 1 is 0, 0, 0 dash, and we have this one is 1, 3, which is 0, 0 dash 1. Okay, we have 2. We have 2. From these 2, we have to take the minimum to cover this. You have to take the minimum number. The minimum number, the same rule as used in the Karnaugh table. When we have boxes, we have to take the minimum number. Here is the same. We have to take the minimum number that cover this. The minimum number that's cover this mean term. Let's cover this mean term. We have only one mean term. We have to take the minimum, and second, we have to take the smallest. What means the smallest? With the fewest variables. In this case, we have 3 variables here, and we have also 3 variables here. In this characteristic, they are equal. They are equal. The 2 covering 2 variables. If in the case we have, for instance, a prime implicant with 2 dashes and 2 variables, we will take this one because it contains only 2 variables. You have to take the smallest one. Anyway, in this case, the 2 are equal. The 2 are with three variables. Okay, and we have to take the minimum number. The minimum number, if we take this one, for instance, this one is covering this. Or we can take this one, the same. Here, it's the same solution, it's the same result. We have two equal reduced solutions. You can take this one or this one. The two solutions are correct. Okay, in our example, we will, for instance, take this one. This one is covering this, and we will not take, we will eliminate this one. And this is the solution. The solution is this. We have what we choose here, and we have the essential. All the essential cannot be deleted. We have to use all the essential prime implicant, and what we choose from a non-essential prime implicant. We choose, here we have the best choice. The choice that the minimum number of implicants that covers all this group. And of course, you have to choose with the minimum number of variables. In this case, we have 3 in the two cases. Okay, this is our solution, this one and this one. We can write the function here, the function of 4 variable a, b, c, d. It's equal to, okay, let's start with this one. This one, we have a deleted, we have b bar because it's 0, c 0 bar, d is 0, that means bar. Or, this or is related to the SOP. We are using the mean terms. This one, the same, we have a is deleted. We have b bar, c without bar, d without bar. Very good. This one, the same, we deleted the a and we left with b without bar, c without bar, and d bar. Or, we have to continue. This one is 13. We have all the variables. We left this one to the end, to the last. This one would be the last. Let's do this. Let's do this. This 0, 1, we eliminated the d. We eliminated the d. We have a, b, c, all bar because they are all zeros, and we eliminated the d. Or this one, which is a, b, c bar, d. And this is our reduced function. You can verify, you can compare that with the Karnaugh map, you will find the same result. You find exactly the same result. And that is it. This is our method for reducing using Quine-McCluskey method. Thank you very much.